Hi, this is part 2 of a two-part lesson on wave optics. In this lesson, we'll talk about additional consequences of the wave nature of light and diffraction. In the last lesson, we talked about diffraction and interference patterns. All the images that you see in this video are attributed to OpenStax College Physics, published by openstax.org under the Creative Commons Attribution License version 4.0. So in the last lesson, we talked about when light passes through a single slit, when that slit is sufficiently small in width, the light will be diffracted and you'll get a diffraction pattern if you project that light through the slit onto a downfield screen. Well, it turns out that this diffraction and diffraction patterns occur regardless of the shape of the aperture, whether the aperture is a slit or the aperture is a circle or the aperture is a hexagon. If the aperture is sufficiently small relative to the wavelength of light, you'll get a diffraction pattern. So in this slide, what you're looking at are what the diffraction pattern would look like if you shine light through a circular aperture that's sufficiently small. You'll get a bright spot, a central bright spot, but then you'll get this halo of bright fringes, almost like a bullseye, that emanate out from the central bright spot. So what this means is that if you're looking at light from two different objects through a circular aperture, say the aperture in a microscope or something like that, if the objects are sufficiently close together, you won't be able to tell them apart. In other words, diffraction limits the resolving power of optical devices, and the ability of us to distinguish two separate objects is limited by this diffraction that occurs. So we can actually write down an equation that can tell us the resolving power of an optical instrument, and it looks like this. The minimum angular separation between two objects, and we're still able to tell the difference between those two objects, in other words, to resolve those two objects as separate objects, is theta equals 1.22 times the wavelength of the light emanating from those objects divided by big D, which in this case is the diameter of the circular aperture through which we're viewing those objects. So this equation is called the Rayleigh Criterion. Have you ever noticed that when two sheets of glass are pressed together, you might see rings of light and dark spots created on the surface of the glass, like is shown up here? Or have you ever noticed that when a thin layer of oil or soap is on the surface of water, you may notice a rainbow of colors on that film? Or did you ever notice this rainbow in the film of a soap bubble or a bubble floating through the air? All of these phenomena are a result of interference. This type of interference is referred to as thin film interference. So what's happening here is demonstrated by these figures up here. And what happens is, as light passes through a layer, a thin layer, transparent layer of some material, it undergoes refraction. And not only that, but at each boundary, some of the light gets reflected. So you have refraction and reflection occurring at each boundary between the air or water or whatever the surrounding media is and the thin film of material that we're interested in, whether that be glass or, in the case down here, soapy water. So the net effect of these various reflections and refractions is that the light that was incident on the thin layers is now split into several different waves. So one light wave comes in, and because part of it's reflected but part of it's refracted and transmitted, the wave is separated into two waves. Well, as is shown in these diagrams right here, those separated waves, which were originally one and now are two or more, travel different path lengths. And so just like the situation in the previous slides, in the previous lesson, with two slit and many slit interference patterns and single slit diffraction patterns, because these waves travel different path lengths, when those waves arrive at the eye of an observer and fall upon the same spot on your retina or a screen, those waves can interfere with one another constructively or destructively. And whether the interference is constructive in giving a bright spot or destructive in giving a dark spot is a function of the path length difference, the distance, the extra distance one of the waves traveled compared to the other, and also the wavelength of the light. And it's also a little bit more complicated than that, because when reflections occur, depending on the indices of refraction between the two materials, the reflection can be a soft reflection or what's referred to as a hard reflection. And during a hard reflection, the wave is shifted 1/2 wavelength or 180 degrees. So all of these things combine together, but in general, thin film interference is a result of light passing through transparent materials, thin layers of transparent materials that have different indices of refraction. So the wave is split into multiple components, and because those components have path length differences, they can interfere with each other constructively or destructively, giving bright bands or dark bands in an interference pattern that can be observed. Now, your textbook goes into more detail in regard to thin film interference, and actually gives equations that you can use to describe the connection between the path length differences, the thicknesses of the layers, the wavelengths of the light involved, and the indices of refraction of the materials that are involved in this phenomenon. But I'm not going to do that here. See your textbook for more details. Do you own a pair of polarized sunglasses? Perhaps they're fishing sunglasses, and when you wear them, you notice that the glare on the surface of a lake is significantly cut out when you wear these polarized sunglasses. So what the heck is going on? Well, polarization is another consequence of the wave nature of light. As we'll learn later in the semester, when light propagates through space, it's actually propagating as an oscillating electric and magnetic field. The electric field represented by the letter E, magnetic field represented by the letter B. And these fields oscillate perpendicularly to one another, and also perpendicularly to the direction of travel. So why does this matter? Well, electric fields interact with electrons, and if we think about a more simplistic example of a wave, let's say a wave on a string. If we set up a string in such a way that the string passes through a rectangular aperture, and then we create waves on the string so that the disturbances in the rope line up with the width of the aperture, the waves can get through. But if the disturbances in the rope are perpendicular to the wide dimension of the aperture, when the waves get to the aperture, the waves will get stopped and the waves will not get through. So polarization of light is a similar type of phenomenon. You see, there's certain materials called Polaroid materials that interact with the electric field component of the light when the light passes through them. So these Polaroid materials tend to be long chain type molecules like this. And what happens is if the electric field comes into this material and the oscillations in the electric field are along the same axis as the molecules, then the energy of the electric field gets absorbed and dissipated by these molecules. The electric field causes electrons to oscillate in these molecules, and that absorbs the energy of the wave, and the energy gets dissipated along that axis. On the other hand, if the wave of light comes into this material, this Polaroid material, in such a way that the electric field is oscillating perpendicularly to the orientation of these long Polaroid molecules, the electrons in the molecules are not excited and they do not absorb the energy of the electric field, and it can pass right through. So a Polaroid material has a specific polarizing axis, and components of an electric field that pass through this material that are lined up with that polarizing axis will get through. But all the other components of the incoming light get removed. So this is how polarization occurs, okay? And in class, I'm going to show you I'm going to demonstrate some polarizing filters for you. It's really hard to do in video form. It's better to do in real life. So I'll show you Polaroid films in action in class. So what's happening with light when it strikes the surface of a water, sunlight reflected off the surface of a lake, for example? Well, what's happening is the light from the sun is largely unpolarized, which means the oscillations in the electric field are randomized and in all directions. What happens is when the light strikes the surface of the water, some of the light gets transmitted and some of the light gets reflected. And it turns out that the light that gets reflected is partially polarized and has a bias in the direction of the oscillations of the electric field. So what you do is you wear glasses that have a polarizing a Polaroid material in them, and the axis of that Polaroid material is perpendicular to the axis of the electric field that's reflecting off the surface of the water. So the filter in the glasses filters out the reflected light, this partially polarized reflected light, and only sees light reflected off of objects underneath the water. So the glare caused by reflection off of the surface is greatly reduced. So this concludes my video lessons on wave optics. And again, in class, we'll look at lots of demonstrations of wave optics that I'm not able to do here in video form.